Thank you for joining us here and giving the first talk in our room. The talk is called, Nikolai already had to laugh because he thinks the title is very interesting, and I also have a question about it. So you're going to talk to us about trade-offs, bad signs, and polar bears, the world of Java optimization. I'm mostly interested in the polar bears there. I'm really wondering what are they going to do, but I guess that's for us to find out, right?
Yeah, and that just to sort of set expectations, the polar bears only come into the talk quite late, and I get nearly to the end, and then I realize, wait a minute, we haven't actually got to the polar bears, and people are only here for the polar bears. So
that's perfect, and people have to stick around till the end. That's how it should be.
Yeah.
So,
but there are polar bears, I promise.
All right, excellent. We've already, I think, got a few viewers and a few people on the stream. Maybe Holly, before we get started with the stream itself and with the talk, can you give us a little bit of background, sort of where you come from, what you've been doing, what sort of your focus is, and yeah, just so we get a bit of context for the talk today.
Yeah, so this talk sort of combines some work I did quite a long time ago and a background I have as a Java performance engineer with thinking that I've been doing more recently about how do we optimize the cloud and how do we make sure that we're using our data centers in the most efficient way possible, because actually if we don't use our data centers in an efficient way, the climate impact of that is really quite large. So data centers use about 1 or 2% of the world's electricity, and really sort of as software engineers, that's on us. And so then we kind of, I think have this sort of obligation almost to say, well, how am I contributing to that? Is I have to do my job, but is there a way for me to do my job in a way that's less wasteful, and so I can reduce that environmental impact? And like a lot of these environmental things, it's actually a win-win as well, because if we make things less wasteful and if we make things more optimized, nobody's going to come back to us and say, oh, this application runs twice as fast as it used to before. I'm so angry with you, right? Everybody's happy. We just have to build up the skills to be able to do it.
Oh, cool. I didn't realize there was such a social significance also to the talk and behind the idea. We just had a big election in Germany, and we had a big climate strike, I think worldwide, right? The climate strike on Friday. So it's also topical, I guess, in that sense. Something to talk to my daughter about and tonight when we went to Accenture today. Yeah, so thank you for the intro. And then I would say we have the talk pre-recorded. So to everybody in the stream, we're going to play a pre-recorded talk. So that's just easier and technically a bit less stressful for everyone involved. Let's see if I can get this video playing, and we can get started with the talk.
Hi, let's talk about trade-offs, bad science. In other words, let's talk about Java optimization. The first question is, why is this interesting? Why would anybody want to optimize? Why are we even here? A lot of it has to do with users. It turns out if things are users get cross, and that costs money. Google did some research many years ago, and they a half a second extra time to return search results meant a 20% drop in traffic. That's a significant number. More recently, Akamai found there was a half a second latency on the page. That's pretty small. You'd see a 7% lower conversion rate. So there's this direct translation, the speed to the money. And then, of course, sometimes it's really directly related. For the high frequency algorithmic trading, what they find is if they have a 10 million delay trades, because of the price shifts, that can mean a 10% drop in revenue. That's huge. So that sounds like we definitely want to do this optimizing thing if it's going to make us save us money. What is optimizing? I often think of optimizing as just make it go faster, but it's not really that simple. We need to think about who is it going faster for? When is it going faster? Is it going faster overnight? Is it going faster in the day? And what is this person who wants it to be faster doing? Are they gaming? Are they actually algorithmic trading? Are they trying to buy something on a web page? That's going to change what faster means. And I've spent many years in the IBM garage, and one of the things that we do in the garage is we combine extreme programming with lean with design thinking. And I find that the design thinking part of it is so useful, because once you look with that lens, you realize it applies almost everywhere. So even something that seems kind of low level and technical, like performance, is still really about people, not about computers. So performance can mean all kinds of different things. Often when we sort of think about performance, our first thought is throughput. So for example, with my broadband, I think, well, have I 200 megabits per second? And if so, that's fast. Otherwise, maybe that's not fast enough for what I need. Or something like transactions per second, that's a throughput measurement. But often, what we actually care about is latency. So with my broadband, I just assume that it's going to come back fast. But if it doesn't, I start to get really annoyed. And things like startup time are kind of a measure of latency. When I start my application to debug it, do I have to go get a cup of tea while it's coming up, or is it just that? If I hit a web page, do I feel like it's responding to me, or is it taking a long time? And if I start a system for the first time, how long does it take before it's really properly productive? How long does it take to up? Another measurement which sometimes is capacity. So the most obvious example of capacity is footprint. So what we really mean by capacity is how many of these things can I run? How many of them can I fit into the same place? And so that's where footprint comes in. A related measurement is CPU usage. So for example, when I'm running Slack on my machine, sometimes it takes 100% CPU. And at that, if Slack itself is pretty responsive, I'm pretty annoyed because I can't do anything else on my machine, and I kind of wanted to do work on my machine. Another sort of closely related metric is utilization. And utilization is really interesting because good goes in both directions on utilization. So when we talk about mainframes, for example, one of the reasons that mainframes are so incredibly efficient is they have high utilization that x86 machines can barely dream of. And so in that context, utilization is good because it means we're using as much of the system as possible, which is good because we've paid for it. Other times, so for example, with Slack on my machine, utilization is bad because I want to use my machine for other things. So you can see even from this short conversation, it's sort of a little bit complicated what faster means. And we do need to just sort of step back and say, well, let's not optimize throughput. I should actually be optimizing latency. There's a great illustration of throughput, which is really true. In the 1970s, there was 2 NASA sites, and they had a data link between them. So it was, a wire, and it broke. And they needed to get information between these 2 sites. And so what they did was they took all of the tapes, they put them in a station wagon, it was white. And then they drove it. And this seems like a ridiculous way to transport data. But the funny thing was, it was actually higher output than they were getting on their data pipe. And that was many years ago. But even now, to transfer really large volumes of data, you want to put it on a tape and move it somewhere. And this is called SneakerNet. And so, for example, this is how Netflix move a lot of their assets, because they're just too big to go over the wire. And all of the cloud providers, if you want to do a really big upload into the cloud, you don't do it via the internet. You put it into you put it in an envelope and you put it in the post to the cloud provider. That's great for large data uploads. I certainly wouldn't want to play a computer game by putting my next move into an envelope and sending it off in the post, because the latency is disastrous. Another thing about these requirements is that they change. So it may be that we used to need to focus on latency and focus on throughput, or the other way around. I heard a story from some colleagues, and they had to debug a problem that a bank was having. And they had this system that had been designed for the tellers to use it once at the end of the shift. So they had a fairly small number of tellers. At the end of the shift, the teller would push the button and it would hit this API endpoint. And then the next day, another teller would hit the button. So it was a gentle transactional load. But then at some point, another team discovered this API, and they were doing a mobile application. And of course, there's a lot more mobile applications than there are tellers. And the way people use this application is, they tend to use it more often. And the way the mobile application itself worked as well is it refreshed every few seconds. So you can imagine what happens. This poor API gets this sort of barrage of traffic, and it starts smoking, and then, it smokes a little bit more, and then eventually it just falls over. So we sometimes say slow is the new down, but of course down is the old down. It was really bad. And the problem was that the original system design was fine for the context. It's just changed. Nobody did anything really wrong. There just wasn't enough communication about the performance requirements. And the world changes as well. So even if nobody starts using our system in different ways, even if, we didn't forget to talk to someone, the definition of good just always alters. So you may have heard of this thing called the cloud. It used to be, for a Java application, the maximum footprint didn't really matter. It was running in a data center. It was probably running in its own machine. It made sense to use those resources. When it's running in the cloud, you tend to pay the footprint. So all of a sudden, that just is money, and you really need to work on optimizing your footprint. I used to work as a performance engineer on the OpenJ9 VM. And recently it was open sourced, which was really cool. And I always knew it was a cool and fast JVM. And it's been really amazing to sort of now see a lot of chatter on Twitter and that kind of thing saying, oh, I tried OpenJ and it was so fast. But here, like with anything else, the definition of fast sort of depends on your perspective. So J9 starts really fast compared to Hotspot. So for this benchmark, it started in half the time. And the footprint is tiny. So the footprint is half. So you say, great, why isn't everybody using this? Well, for this particular benchmark, if you look at throughput, after it's just started up, the one that had started obviously gives you better throughput, and it ramps up to its maximum capacity faster. But if you leave it running for long enough, Hotspot will give you a little bit better throughput. And we now see sort of versions of this trade-off in other places as well. So you may have heard of Quarkus. Quarkus, it's a little layer that wraps around the JVM, and it trades off flexibility against startup speed and against footprint. So Quarkus basically starts ridiculously fast, and it uses ridiculously tiny memory. But there is, the programming models that you have access to is a bit more restricted. But I heard a story about, we had, Red Hat were at a conference, and they were demonstrating Quarkus at a booth, and they had all sorts of people at the booth, not just the technical staff. So one of the project managers was on the booth, and he, would demonstrate Quarkus, and then, the person would go away and he'd demonstrate Quarkus again. And perhaps he wasn't using it all day, every day. There were some basics that he did, like when you finish doing a demo, you shut it down. And at the end of the day, he looked at his machine, and he had 120 instances of Quarkus running on his laptop. But the thing that I like about this story is he hadn't noticed. It didn't make any difference, the fact that he'd, done this sort of rookie error and forgot to shut things down. And you may think, well, okay, I may be different, but I don't really care about the ability to run 120 instances of something that I'm no longer using. And it's sort of natural to optimize for the cases where something is being used, rather than the cases where it's not being used. I think it actually does make sense to optimize for those unused cases as well. Most of what is running in our data center, or not most, but a good fraction of what's running in our data centers is what's called zombie workloads. So these are things that maybe were useful once, but they're not being used anymore. And they're just sat there searching along, using CPU, using memory. And so it makes sense to make those zombies as efficient as possible, as small as possible. And I've seen different estimates of how many workloads are zombies, but it's somewhere between 25% and 30%. So that's significant. So hopefully at this stage you're sold. You're saying, okay, why optimizing is important, and I definitely want to do it. Where do I get started? Turns out it's easy. What you need to do is you need to find the bottleneck, the point where the resources are constrained, and then you just fix that bottleneck. And then once you've done that, you can go on to the next bottleneck and the next. But there are some pitfalls on the way. And the first pitfall happens when you're trying to find the bottleneck. Because what most people do, including me, is we have an intuition. We kind of know that this thing is just a bit slow. It's slowing everything down. Ideas are great. Intuition is great. Performance tuning, optimization is not the place for ideas. Leave your ideas at home. The thing to do with performance, you'll see this written a lot, it's really important. Don't guess. And of course, it's not to just measure any old thing. You have to figure out what the right thing to measure is. And probably that should be what your users care about. So if they care about latency, measure latency, don't measure throughput. And we can get into trouble with, even if we're measuring though, I think we can get into trouble because we can sometimes sort of do this blinded by science thing where we're sort of dazzled by numbers. And if there's numbers in something, it makes it look legitimate. I have numbers, I must be doing the right thing. Well, no, if there's numbers in it, you need to sort of check. Is this the right thing? Is this what my users care about? And you need to look beyond that into things which influence it. So I'm going to do a little digression into business theory, but I think it's interesting. Two kinds of metrics: leading indicators and lagging indicators. Lagging indicators are what your users care about. So we care a lot about indicators. Lagging indicators are easy to measure. How much money did I make? What's my churn rate for my customers? The only problem with lagging indicators is they're hard to change. We don't really know what's going to make us make more money. We don't really know what's going to retain our customers. And this is where the leading indicators come in. Leading indicators are easy to change. What color is my website? Am I running on Java 6 or Java 7? I mean, it's 2021, hopefully neither. And leading indicators, they're predictive of a thing we care about. So the color of the website determines how happy our users are. But the only problem with leading indicators is we don't actually know what the right leading indicator is. Should I be measuring the color of my website? Or should I be measuring what font I use? Or should I be measuring, we don't know. So the trick is to try and get those leading indicators that influence the lagging indicators and get them all identified. I want to show a few little to sort of show some of the relationship between the things we can change and the things about. All performance experiments, when you see someone else's performance experiment, treat it with caution. It's context sensitive. Here particularly, treat these are for entertainment purposes only. I should add as well, actually, they're not entirely demos because I didn't want to do performance demos live because the software uses so much CPU that it kind of throws off the results of the performance experiments. So about 14 years ago, I did an MSc because IBM would, and I thought if IBM paid for it, great, I will take it. And so I did it on garbage collection, just continuing the work that I was doing for my day job anyway. And one of the things that really annoyed me at the time is that there's this persistent bad take, which is reducing time spent in garbage collection to improve the performance of your application. And the way you want to tune your GC is to reduce the time. But the thing is, an app does lots of things that involve memory access, and garbage collection rearranges memory. And sometimes rearranging that memory makes the app faster. So time invested in garbage collection can give big rewards. So one of the ways to make memory access faster and to make garbage collection much, much slower, to compact the heap more. So I did sort of this really, what should be a dreadful optimization, which is I told it every time it does a garbage collection, do a compaction. You can see the blue line is that, and it spent way, way more time paused, and the pauses were longer. But if you look at the throughput of my application, you can see that even though I had really stupid GC behavior, my throughput was better. My application processed more transactions if it compacted all the time. So even indiscriminate compaction can give you performance benefits. So I started to use this experiment. So obviously a lot of things have changed. I used a slightly different benchmark and I was on a much newer version of the JVM. So I took a benchmark called Day Trader and then I used JMeter to drive through it. So the first parameters I tried was this. So I turned on verbose GC and then I selected every GC. And what I found was that I wasn't seeing much difference with and without compaction. So I changed my GC to one that's called opt throughput and actually made the throughput slightly worse because naming things is hard, especially if you have to keep the same name for 10 years. Still didn't see much difference with the GC. I could see that my pauses were longer, but nothing else. So I thought, I need to make my heap smaller. So I made my heap artificially small. Compaction still didn't change the throughput. I set my heap to be medium size. Compaction still didn't change the throughput. I set my heap to be huge. Compaction still didn't change the throughput. So I should add as well that, of course, this is cheating. This is the bad science part, because
trying to look in a haystack for the exact set of parameters that prove your point. That's not science, that's the opposite of science. Science should be doing experiments that try and disprove your point, and only if you can't disprove it do you think, okay, I think it might. So eventually I found a change that managed to affect my throughput. So you can see here I'm plotting time spent in GC, and I'm using a tool called GCMV, which is a popular memory tool, and I also wrote it, so I kind of like it. And I have two scenarios. In the first scenario, I spent 21 seconds in GC. So that was about 4% of the overall application time. With my change, I only spent 12 seconds in GC. So it was only 3.6% of the application time. So, sounds great. I've reduced the load. It's not that simple. When you look at how much garbage was collected, the case that didn't do much in GC didn't collect garbage, whereas the other one was working a lot harder. Why was the GC working so much harder? It was working harder because it had more to do. It had more to do because the application was doing way more. So I had almost twice as many transactions per second. So I spent almost twice as much time collecting the garbage from those transactions. So it's actually the high GC case. That's the good one. And then let's think about this in terms of leading and lagging indicators. The time spent is a leading indicator for the thing that I actually care about, which is my transactions per second, and that's the lagging indicator. And the sort of surprising thing is that the direction of correlation is counterintuitive. Instead of less time in GC meaning less performance, less time in GC means more performance. So I need to be really careful about what I use my indicator for and how I tune it. And then even that lagging indicator, I need to be kind of cautious about, do my users really care about transactions per second, or should I be optimizing latency? And there's one thing I didn't mention, which is what did I do to make that application go faster? Was it a clever GC setting? Actually, it wasn't. It turns out, everybody always says, never, ever, ever, Performance 101, never run your load, so JMeter, on the same thing as the thing you're testing. For me, I've got a lot of CPU on my machine, so the network was the bottleneck. As soon as I had JMeter and my workload on the same machine, I got twice as many transactions. So that goes to show that you always need to be careful with performance advice. And it also shows that I so long tuning and detuning that GC, and I wasn't on the bottleneck. So any change I made there didn't actually affect anything. And like I said, it shows that all advice needs to be treated with caution, even if it's my own advice. So what should you do? Well, do know that GC can improve performance by rearranging the heap. Always, always, always find the bottleneck. And always, always, always validate performance advice independently. Because advice can be, it seems like such a good idea to not try and reinvent the wheel. But performance advice can be really treacherous. So many people who are wrong on the internet about so many things, but especially for optimization, because last year's good advice is this year's awful advice. So people used to say, and you can still find it because the internet remembers it, to make your Java go faster, make one big method, because method dispatching is really slow. This was true in Java 1. It hasn't been true for years and years and years. And making your methods modular improves the readability, improves maintainability, and it actually makes it go faster because the JIT can do its job. Another thing that people used to say is you should reuse your objects. help the garbage collector because it means you don't have to garbage collect them. That's kind of true, but it turns out that for most modern garbage collectors, if something dies young, it's basically free to collect. It just sort of goes away. And if something lives for a long time, it's really expensive because every garbage collection, it has to be moved around. So this advice, just don't. And when you look at tuning the JVM, there's a lot of command line options, and it can be a bit overwhelming to try and figure out which ones you need. And so a lot of people will try and find answers on the internet. What's the magic incantation that makes my JVM go faster? Well, of course, if there was one, we'd all be using it and it would be the default. But we still get this kind of folk wisdom that gets passed forward of this is the command line that makes this work faster. And when you look into them, often you'll see that some of the options are contradictory, some of the options are obsolete, and some of the options are definitely going to slow things down. So what about this one? You should use string builder rather than concatenating strings. So this one's a little bit more complicated, right? Because we all know this is true. It's true, but it with caution. Because we all also know that premature optimization is the root of all evil. So when you look at advice, be aware how old the advice is, but also look at your own context. Because otherwise what you risk is micro-optimization. Jeff Atwood, he wrote a lovely blog called The Sad Tragedy of Micro-Optimization Theatre. And like a lot of these other theatres, what he saw was that people were doing things with lots of sort of noise and activity. And the intention was to make something go faster, and it looked like it was making it go faster. But when you looked at the big picture, no effect at all. A bit like my GC optimization. So he gives this example, which is we all know a string like this or a sequence like this is disastrous in terms of performance. What we should be doing instead is using a string builder, because every time we concatenate onto that string, it has to make a whole new string and then copy stuff. So I'll prove this advice. So I looked through my little benchmark and I found a case where it was using string concatenation inside an iterator. And I thought, I'll optimize this. So it was a bit like my GC experiment, but it was even more disappointing. I ran it, no change whatsoever. And when I looked into it, I realized this method never even gets called. It was a two-string method, so it didn't matter really what the performance was. And not all cases are as extreme as that, but a lot of the time, it's not worth that slightly worsened readability for something that doesn't affect the performance. And we see this in code, and we see this in life as well. And I sometimes think of it by analogy with when I travel. When we traveled, I used to always try and be ecologically conscious and, minimize carbon footprint. So I would never take a taxi to the airport. I'd always try and take public transport. And sometimes that was really slow and expensive. But I felt really good about myself for doing it. But the problem was I'd feel really good to the airport feeling good and then get on a plane, which completely overwhelmed any benefit from taking the taxi or not taking the taxi. And you may think, okay, yeah, but surely I'm better off taking a taxi and a plane, or taking public transit and a plane than taking a taxi and a plane, right? Because every little helps. Well, sort of. That sacrifice to take public transit maybe gave me such a good feeling that I didn't have enough sort of sacrifice budget left for other things. So we always need to look at the opportunity cost, because we don't have infinite time and infinite energy. And a lot of these things where we work really hard and make a sacrifice to try and tune it, we don't even need to be doing at all, because our platform will be tuning it for us under the covers. So in this case, As far as I know, this will still be slow in terms of its performance. But if it was something like this instead, where it's not in an iterator and it's a bit more well-defined when it ends, this will get optimized away to be a string builder under the covers. So we don't need to worry about optimizing it. And in general, the people who write the JVM have way, way more time to optimize the JVM than you do to optimize code. So what we want to do is we want to be on their golden path. And what that means is that we want to be writing clean code, because that's a good idea, and typical code, because it comes back to that design thinking and who are we optimizing for? They're optimizing for people who write typical code. You be one of those people. Okay, but what if your code's not typical? What if your use case isn't typical? You need something more default, because you can see you have a problem. No amount of talk about defaults being good enough helps, because the default isn't good enough. So you're going to need tools. And the reason you need tools is because you need to know what's going on. What you can optimize is limited to what you can observe. So now we'd sort of talk about this in terms of observability, of I need to be able to interrogate my system and figure out what's going on. And there's a whole bunch of tools, more than I could list on one slide, that maybe are going to help with this. So you want things like a method profiler. Visual VM is a good one, it's free. Mission Control is also a good option. IBM Health Center also free, so that's just for OpenJ9. Another thing that you should look at is flame graphs. So none of these tools really do flame graphs, but flame graphs are incredibly cool as a way of visualizing what time is spent. If you see that the problem has to do with GC, or even just to rule out GC as a problem, you're going to need some GC analysis tool. I mentioned GCMV already because I wrote it. For heap analysis, if you figure out that I've got a memory leak, I've just got way too much in my heap and I need to try and optimize that, there's a tool called Eclipse MAT, Memory Analysis Tool. That's a good starting point. You need something that's a bit more of a kind of an integrated package. So then you want application performance management tools. So Glowroot is a good open source one, and then there's a bunch of proprietary ones. So New Relic, AppDynamics, Dynatrace, all really good. But of course, in 2021, your system's unlikely to be just a single process. So you're going to have interactions between different systems. So at that point, in order to make any sense of it, you're going to need some kind of distributed tracing like Zipkin or Jaeger. And I mentioned distributed tracing, and that leads us to sort of an interesting question, which is, if I have a microservice architecture and I optimize a microservice, is that just micro-optimizing? And does that mean I shouldn't be doing it? If I don't do it, where do I even go? Because if you assume a team responsibility for a single microservice, surely that team spends some time in optimization. And it's a bit like the example earlier from the bank. You need to know how your things are being used, and you need to know that broader system context in order to know whether you should invest your time in optimizing, which clearly for this bank application they should. They spend a little bit of time optimizing it and they manage to get the problem just vanished once context. Or is your microservice the equivalent of a toString? It doesn't really matter how slow it is. It only gets called overnight. Another thing to consider is that when you look at the performance of your system, it's quite tempting to look at the average and to say, my average transaction time is this, my average throughput is this. That's possibly not what you should be looking at, because if you have outliers where people are really unhappy, they will let you know. And performance theory is quite closely related to queuing theory. And what queuing theory tells us about is the distributions of things. And what happens if this is slow and then this is slow and then this is slow? And that's where we start to get those sort of performance disasters, where for most users it's fast, but if someone hits the slow case, it takes them a day. So you always need to be looking at the edges, not just the averages. And this is something that I think professionals know intuitively, but for those of us who have other day jobs and other specialisms, it's something that we sort of have to learn, which is amateurs look at averages, professionals look at distributions. When we think about observability and impact, I just want to talk about cloud and cloud costs as well. Because often excessive footprint, excessive CPU usage will translate into a big cloud bill. But often on the engineering floor, we don't have visibility of those cloud bills. So if we can get those cloud bills sort of routed to us, that helps. So Spotify, for example, do a really cool thing where they put their cost usage, their cost metrics into their engineering dashboard so that engineers can optimize those things as well as optimizing everything else. But what about the polar bears? We haven't got to the polar bears. Well, a while ago, my kids, they probably like all kids, they're really hopeless at watching TV, and then when they're done, they just wander away and leave the TV on. And eventually I'd had enough and I snapped, and I pointed out to them that every time they leave the TV on, a polar bear dies. This is a slight exaggeration, but only a slight exaggeration, because we do have a problem where the amount of energy we're using is changing the climate, which is impacting species like polar bears. Although I don't recommend this as a parenting technique. And more generally, because waste has such an impact, I think we have a moral obligation to avoid waste. And that means two things. We should use no more electricity than we need, and we should also try and use no more hardware than we need, because the hardware is actually where a lot of the carbon comes. But the electricity itself uses a lot. So data centers use around 1 or 2% of the world's electricity. And then on the device side, manufacturing a device uses an incredible amount of energy and an incredible amount of carbon. So when we think about what we do with our IT, we should really try and do the same with fewer devices. So then that comes back to that footprint conversation of how do we increase our efficiency? How do we lower our footprint? And how do we support more tenancy? So with Kubernetes clusters, a lot of them are really single tenant. And that's just so inefficient. And then the next thing we want to do is we want to try and figure out how do we make these systems last longer. So this is partly a hardware conversation, but how do we sort of end that plan essence that means we throw everything out every 3 years and try and make systems that are designed to behave gracefully for longer. So I'd encourage you all, both for the polar bear moral reasons, but also just because it's fun and satisfying, to look at optimizing, see what you can optimize, get that toolbox so that you're able to optimize when you need to. And the first thing in your toolbox should be solid ways of rather than just guessing and risking misguided optimization or micro-optimization. Because ultimately, only optimize what matters, because time is also a limited resource. With that, I'll stop, and I'm really looking forward to your questions.
So, Holly, thank you very much for the talk.
Yeah, my pleasure. I had lots of fun writing that talk.
Yeah, I'm glad to see that the polar bears did make it into the talk at the end, but I was a little bit shocked about the strategy for dealing with the television problem with the kids.
Yeah.
I'm considering using it. I'm not sure if they're going to be crying or not on the end of the kids. Did it work?
I think it might have actually. It didn't completely fix the problem, but I think we went from maybe like 100% leaving it on to maybe 50% leaving it on. So
Right.
every little helps.
Excellent. Yeah, so that's something we can take home at least today. You've also been hard at work answering questions in the chat. So there's not too much from the audience, I think, that's open. I think at least the questions that were coming up there were answered. There's one in the Q&A, but I wrote down some things that I wanted to talk about as well. So if anybody in the next 13 minutes has questions for Holly, feel free to add them to the chat or the Q&A. I will pick them up and repeat them here. But in the meantime, I was wondering, you talked a lot about the hows and maybe also the whys and how to approach performance optimization, and especially with measuring, and lots of good advice. I was wondering, do you have some thoughts on if you're like a normal developer, you're working on an application, maybe it's cloud-based, maybe it's not. Are there good ways to integrate this kind of performance or optimization thinking into your daily work? When's a good place to start with that? When's a good time to do that? Do you have some thoughts on that?
Yeah, and I sort of go back and forth on this a little bit, because increasingly now, we're all expected to wear so many hats and have so many different skills. So we need to be able to do the application programming, and now probably we're being asked to be a full stack developer, so that I can do the back end and I can do the front end, and then we have to be a DevOps engineer as well, because definitely that's something that we should be doing rather than having a separate DevOps team. And then now with the way we run applications, we really need to be infrastructure engineers as well. We need to know Kubernetes, and then to sort of come on top of that and say, oh, but don't forget, you need to be a performance engineer as well. At some point it just becomes I can't do all this. I only have limited mental capacity. And so then there is sort of the question of like, at what point do I think about it? And if one of the conversations that we sometimes have is at the beginning, let's think about our performance requirements. Like, should we invest our precious resources optimizing this, or is it actually something that doesn't matter and we wait till we have a problem? And what I'd kind of suggest is a hybrid approach, where we do sort of a lazy effort on performance awareness at the beginning, but we then wait to see if we have a problem and wait to see if we have requirements. So what I kind of like to do is build a little bit of light performance monitoring into my DevOps pipeline, so that I run some tests just to see, okay, well, if things get radically slower, can I trace it back to the change that happened? But it needs to be, it's hard to do that, because if you are running something else on the same system as you're running your performance tests on, your results are unreliable. With the cloud, we're always running something else on the same hardware, so then we just end up with such noisy results. So I think you kind of have to, if you're going to do it in that kind of lightweight way, you have to sort of accept that the results need to be taken with a pinch of salt. And I'm going to have some monitoring so that I can see if my transaction time goes from 10 seconds to 2 minutes.
Right.
But finer grain changes I'm not going to see unless I start to put some dedicated effort in.
I mean, what you mentioned there is really, really hard. I also noticed that in our applications, simply this, you mentioned this example where the network was actually the bottleneck, and moving the loads to the same machine and then eliminating the network made such a difference. That's also such an environmental context thing that often is the case, like such complicated topologies or things in between. So it's really, really hard to pin down on that. But on the other hand, like you say, if you manage to grab, just to pick up on your terminology, one of the lagging indicators, if you're managing to improve those, then it's a big added value. So yeah, cool.
Sorry, I just have a sort of a follow-on thought as well, which is often when we become aware of the problem is when there's a lot of pressure on, so we're about to release, and then someone comes in and says, wait a minute, this performance isn't acceptable. And then if we're sort of at that point going, okay, so I need to learn all my APMs, and I need to learn distributed tracing, and I need to, learn how to analyze performance across the that's not going to be a happy experience. So it's worth front loading a little bit of that learning and trying to build up those skills and learn the tools when it doesn't matter super much. Just so that it's less of a kind of a heart attack moment when we need to do it when it matters.
Absolutely. Yeah, absolutely. You mentioned all these different tiers of tools, like familiar with some of them, and typically a profiler gets used maybe sometimes in development to identify some ad hoc bottleneck. But if you're looking at this whole application, this performance management, AMP, you're talking about this distributed tracing and so on, that's a whole other ballpark, right? That's not something a developer will just install on his machine and just have a play around with. You have to actually think about how can we set this up and do that. So Is that, you mentioned like running performance tests on CI, or at least integrated in the build environment. Is that something you've then also spent time up, sort of setting up a decent, or at least a simplified maybe test environment, and then integrating those tools to get those metrics during CI? Is that something you've done?
Yeah, so in general, what I've done is in CI, I've had it spitting the numbers out. And then when I'm using the tooling, I've usually done that more on a
Okay.
local environment,
Okay.
just because the tools usually cost and the artifacts are kind of bulky, and
Right.
you most often won't need them. So again, it's one of those things that if you have the time and the resources, and you get those, those metrics and that sort of more detailed tracing coming out of your CI, more power to you. But more often, the diagnosis will be a bit after the fact.
Right. Yeah, I totally understand, and that makes it just so hard to identify. So it's something we need to work on, I guess. I also like your point about if you develop and deploy in a cloud environment, that basically the billing is like the fact that you're getting bills, that it's all measured and metered, what you're doing, the power usage, the time that's running, the bandwidth that you're using. It's an interesting indicator of, like an additional signal that you get. Because I've typically worked in more traditional deployments, like customer has some sort of server farm or has his own cluster or whatever and deploys on there. And it always seemed to me, probably it wasn't for the IT department, but it seemed to me like power and resources are sort of, they're there and we can just use them. And it's much harder to get that feedback. So that's actually quite an advantage in that sense, I would guess.
Yeah, it's like both a leading and a lagging indicator. So it's a lagging indicator for the profitability of your business, because cloud bills are often, a big part of the spend of a lot of businesses. So, there you have a direct lagging indicator for the profitability. But then it's also a leading indicator for how your application is doing. Because if your cloud bills jump, that's going to show you I'm suddenly wasting some resources that I wasn't before.
Right. Cool. I just saw that we got a question in the Q&A tab. Let's go to the audience. I think the question is from Dimitri. He's asking, is the app to database network bottleneck either in your setup? I'm not sure. So I'm guessing it's your setup, Holly, that he's talking about, or that he's talking about? I think in general, the application to the database, I mean, I've seen deployments with customers where there's huge, complicated topologies with networks, and it can be a big thing. I don't know how it is for you.
Yeah, I've definitely, the database can be sort of a bottleneck in two ways. So one is just that connectivity to the database, and then the database itself, especially, I mean, once you get into things like stored procedures, then all of a sudden, sometimes your database can it can be this performance catastrophe because you have one evil stored procedure that you hadn't really anticipated, and it locks the whole database, and then nobody else can do anything. So yeah, there's sort of both things to look at. In most of what I was showing, like the database was, sort of a lightweight toy database, so it didn't have, any of that, and it was sort of in process and stuff. But definitely in more realistic scenarios, it can definitely start to be a major cause of performance woes, and a challenging one as well, because then, adding to all the skills that I listed, then all of a sudden you need to become a DBA as well to be able to sort of unpick these subtle database performance characteristics.
Yeah. It starts to add up, like if you mentioned DevOps before, and then performance things, and then database things. It's quite a big set of skills. So yeah, I think in the end we cannot expect one person maybe to be the master of all, but maybe in a team it's possible to sort of have a sort of a load balancing in that sense. Have some people know a little bit more about database stuff, and some people more on the DevOps side. It's hard to balance, definitely. There was in the chat before, and I was also interested because I hadn't heard of it yet. The GCMV tool, I think it's called, right? Is the tool that you wrote yourself. How did you come to writing this, to make this? Is this in the context of your MSc that you did, or how did you come about writing that tool?
So it was when I was working, I used to work on the team that wrote the OpenJ9 VM, and I was a performance engineer in that team.
Cool.
And I was working on the garbage collection performance. And so, of course, the the thing that we spent most of our time doing was looking at the verbose GC logs, and we didn't really have good tooling to do it. So then what I ended up doing was writing tooling for myself. And then, of course, once I'd done that, we thought, well, actually, yeah, we should release this. And it's nice because it was a long time ago now. So 10, 15 years ago.
Whoa.
And most, in the lifetime of computers, most tools sort of, appear and disappear in that time.
Mm-hmm.
And so it's nice to see that, GCMV is still, very much alive and being used.
That's excellent. I will actually check it out, because I think in the domain of garbage collection, you mentioned a bunch of tools with performance, but like analyzing garbage collection logs, and also you mentioned Eclipse MAT, which also has been around for a long time. And I always grab for Eclipse MAT when I want to do heap analysis, but I'm definitely going to try out GCMV, because we need something for that as well. It's something we, at least in my company where I'm working, we very rarely look at GC times and pauses, and it's usually other aspects of performance, like how long does this request take and what happens. And GC is sometimes a factor, of course, but often we're more focused on other things. So that's really interesting. Very cool.
Although remember, if you do use it, don't fall into that trap of just trying to push the GC times down.
Right. I did see that. So the difference between how much time you spend in GC and then in the end the transaction benchmark, that was really very helpful advice. Definitely. I actually wrote down what you mentioned with is find your bottlenecks and validate the advice, because that typical performance advice you get online, if you go to Stack Overflow, you find like some sort of advice there, or maybe some other site, and people say try this, or you just have to do that. That's a very dangerous hole to fall in.
Yeah, there's sort of two things wrong with it. One is just the fact that their context will be different from your context, but then as well, things change so fast, and a lot of, if advice is really good advice, then it does get sort of incorporated into the JVM, or the JVM gets rebuilt in such a way that eliminates the problem.
All right. Oh, cool. Looking at the time, we're sort of approaching the end of the slot, I think, if I have the time correctly. Let me see if Q&A still has something new for us. No, I think... there's one new question, brand new, from Matthias Bünger. He's asking, any advice about how to find the bottlenecks?
Ooh, yeah. So you're going to need, you're going to need tooling for sure. And one of the sort of challenges is that you need to look at the whole system. So there's, this is a bit of a digression. But one of the other tools I mentioned, Health Center, it does method profiling. And one of the things about it is it reuses the instrumentation that the JIT uses to figure out what to optimize. So it's almost free. Whereas most method profiling tools, you have to tell it what to profile. So you have to kind of pre-select where you think the bottleneck is, because that's where you're looking. And in general, when you're trying to find the bottleneck, you have to try and look as broad as possible. So, and as another example, if the bottleneck is the network, but I just run a method profiler, I'll think I found the bottleneck, but actually I didn't look at enough of the system. So, I optimized this one method. So really you want to look at a range of metrics. So you want to look at, well, what's my CPU usage? If my CPU usage is 100%, then CPU is going to be a bottleneck. If my CPU usage is 20%, I know it's probably waiting on file IO. It's probably waiting on network access. It's waiting on something like that. And then, so that sort of gives you a starting heuristic. But then if it's a microservices system, I mean, good luck looking at the CPU usage for your microservices system as a whole. So then you do need one of those sort of higher level system, sets of tooling that will look at your system as a whole and then guide you to the bottleneck without you having to sort of know, okay, well, how do I figure out how to measure this?